This lesson shows two short examples of how to quickly do an analysis using conservation of angular momentum to help answer conceptual type questions. They could be multiple choice questions that read as just conceptual questions, or they could be questions that are part of a larger free response question as well. So, for example, here we are given a case where we're told a rabbit, disgruntled rabbit, it has a merry-go-round invading its territory. So the rabbit charges the merry-go-round with a velocity v, a momentum mv, chomps onto the end of the merry-go-round and the rabbit then will spin together. And a question could be asked about how the final angular momentum of this system will compare to the initial momentum of the rabbit. And rather than just try to kind of think of it yourself with like a gut instinct type of reaction, make a quick calculation to help with those types of questions. As soon as you see the word collision, you should automatically go to conservation of momentum, whether it is a linear or rotational situation you're looking at. You do need to pay attention to some of the specific language in the question. Like here we were told that the rabbit is running tangential to the rim, so that simplifies our analysis because we have a 90-degree angle in here. We're going to look at the initial angular momentum of the system, set it equal to the final angular momentum of the system, and we'll have a nice equation to help answer those conceptual type questions about what the final angular velocity will look like. So initially, all the angular momentum is with the rabbit. The rabbit is a point particle, so that's r cross mv. Remember, you always use r cross p for point particles. Here we have 90 degrees, so we get rmv for the initial angular momentum of the rabbit. It's a completely inelastic collision. They stick together. So you have the point particle mr squared of the rabbit. We are told, or should be told, to assume that the merry-go-round is a uniform disk, so we'll just assume that for our discussion. So disk-shaped, 1/2 mr squared, and that's it, you're done. So your analysis was very short, very quick. You have an expression now for omega final. You solve for omega final. And that initial question about how does the initial momentum of the rabbit affect the final velocity, angular velocity of the system, is now you know it's a direct proportionality. So it's not a square root, it's not a square, and that multiple choice question would be very easy for you. Well, let's take a look at one more simple example. Here we have, here we have a situation where we have a spinning disk, disk 1, this top disk, and it is going to be allowed to fall and collide with the disk below it. The disk below it is at rest, and we are going to allow internal friction, as it says here, between the two to slow down the top disk. So when the friction on the surface here interacts with the bottom surface of the spinning top disk, that friction is going to increase the rotational speed of the bottom disk and slow down the top disk. That will occur, the speeding up, slowing down, until they reach a common final velocity. And again, you could be asked any number of conceptual questions relative to what does the final rotational speed of this system look like. And again, you don't want to just kind of guess at it and use like a gut instinct. L initial equals L final. It's a collision. So the bottom disk is at rest. So we have L equals I omega for the disk. Bottom disk is at rest. That's 0. So all of the initial angular momentum is in the top disk. They reach a common final velocity. It's a completely inelastic collision. They stick together, so that's why it's I1, I2. And again, we can very quickly get an expression for omega final. And typical conceptual questions for this type of system or this type of dynamic might be about the omegas. So again, in this case, the bottom one was at rest, so the direction, the vector direction of the momentum initial has to be the same as the vector direction of the momentum final, and since all of the initial momentum was with the top disk, we know that they have to have the same direction. Again, you have to be careful because they could have given more momentum had they wanted to the bottom disk in the other direction. So had they given us actual momentum values, we would have to look to see which one had the larger value initially to make sure our system momentum is what we are looking at. And the other aspect of this would be how the final velocity depends on the mass of the objects. So, and the mass will affect the inertia because if it's a disk, 1/2 mr squared. And you can see here, this term in the middle tells us how the inertia is going to affect the final velocity. So if the initial disk, the spinning one, dominated the system, so it was really heavy, really big. Now the bottom disk has to be strong enough to support it, but as long as it's strong enough to support it, if the inertia of the bottom disk is insignificant, then the final velocity will equal the initial velocity, and that would make sense, I think, because the top disk would just steamroll the bottom, that light bottom disk sitting beneath it. So I didn't want to, let me erase these, so if you want to copy the clean page down, you can. I didn't want to dwell on either one of these pages too much, just to emphasize a quick analysis with equations where you actually generate a final equation to help you answer conceptual questions is definitely the way to go for those multiple choice questions.